各位觀眾請注意，請勿在場內吸煙、飲食。未經准許，請勿攝影、錄音或錄影。任何人士未經授權而攜帶攝錄器材進入本場所，即屬違法。本場所負責人有權拒絕攜帶攝錄器材嘅人士進入。喺節目進行期間，請關掉無線電話、傳呼機及鬧錶嘅響鬧裝置。多謝各位合作。各位觀眾請注意，請不要在本廳內吸煙、飲食。未經准許，請勿拍照、錄音或錄像。任何人士未經授權而攜帶攝錄器材進入本場所，即屬違法。本場所負責人有權拒絕攜帶攝錄器材的人士進入。在節目進行期間，請關掉無線電話、傳呼機和鬧表的響鬧裝置。謝謝各位合作。
Ladies and gentlemen, may I have your attention, please? Smoking, eating, drinking, unauthorized photography, recording, and filming are not allowed in the auditorium. It is an offense for any person to bring video recording equipment into this auditorium without authorization from the venue management. The venue management may refuse entry of any person who possesses such equipment. Please also switch off the beeping devices of your wireless telephones, pagers, or alarm watches during the performance. Thank you for your cooperation.
Good afternoon, ladies and gentlemen. Welcome to the Popular Science Forum, Meet the Shaw Laureates, the challenges and the joy of doing science. The forum is about to begin. Please be seated. Today, the Hong Kong Science Museum and the Shaw Prize Foundations have the pleasure to present this event. Before the forum starts, we would like to invite both the organizers and the Shaw Laureates 2014 to take a few photos. Now, may I invite our guests to come to the stage. Ms. Karen Seitz, Museum Director, Hong Kong Science Museum. Professor Kenneth Yang, Vice Chairman, Board of Educators, the Shaw Prize and Master of CWGO College, the Chinese University of Hong Kong. Professor Park Chung-cheng, Council Member of the Shaw Prize and Pro-Vice Chancellor, the Chinese University of Hong Kong. Professor Y.E. Chen, Council Member of the Shaw Prize and Director, School of Biomedical Sciences, the Chinese University of Hong Kong. Professor Daniel Eisenstein, Shaw Laureates in Astronomy 2014. Professor Sean Cole, Shaw Laureates in Astronomy 2014. Professor John Peacock, Shaw Laureates in Astronomy 2014. Professor Kajitoshi Mori, Shaw Laureates in Life Science and Medicine 2014. Professor Peter Walter, Shaw Laureates in Life Science and Medicine 2014. Thank you very much. Please return to your seats on the floor. The forum is about to begin. May I invite Professor Kenneth Young, Vice Chairman, Board of Adjudicators of Shaw Prize, to give a brief introduction of the forum, as well as introducing the Shaw Laureates in Astronomy 2014. Professor Young, please.
Good afternoon, ladies and gentlemen. Welcome to this forum entitled Meet the Shaw Laureates 2014, The Challenges and the Joys of Doing Science. The Shaw Prize, established in November 2002, consists of 3 annual awards: the prize in astronomy, the prize in life science and medicine, and the prize in mathematical sciences. It is an international award to honor individuals who are currently active in their respective fields and who have recently achieved distinguished and significant advances or have made outstanding contributions in academic and scientific research or applications, or have achieved excellence in other domains. The 2014 prize was just awarded 2 days ago, on 24th of September, to 6 individuals. We are delighted to have the laureates in astronomy and in life science and medicine with us today in this event. And this event is presented by the Leisure and Cultural Services Department together with the Shaw Prize Foundation, and is organized by the Hong Kong Science Museum and the Hong Kong Space Museum. The purpose of this forum is to let the public, especially young people, meet distinguished scientists up close, to get the first-hand glimpse and personal glimpse not only into the subject matter and the questions at the cutting edge of science, but also a glimpse into the life of scientists. Science is not a dry and abstract activity. It is an exciting endeavor by real people who are in many ways like any of us, but deeply committed to journeys of discovery in which they take great pleasure. I believe most people in the audience have already read the relevant material and have probably watched the presentations on television in the last couple of weeks. In any event, you want to hear it directly from the laureates. So I shall be very brief in placing their works into perspective and in introducing the laureates. The first part of this forum will be about astronomy. We all know that the universe began in what is commonly known as a Big Bang, 13.80 billion years ago. The fact that scientists actually dare to quote this number to 4 figures, and the uncertainty is probably only in the last figure quoted, shows that cosmology is no longer armchair philosophy, but science rooted in detailed and accurate measurements. To put it very simply, astronomers have succeeded in obtaining pictures of the universe when it was very young. If in the audience you are about 20 years old, it is as if someone has come up with a picture of you a few hours after you were born. The Shaw Laureates in astronomy have made important contributions in this regard, with reference to what is called the baryon acoustic oscillations and the redshift space distortions. Speaking to us today, in turn, will be the 3 laureates in astronomy. They are Professor Daniel Eisenstein, Professor of Astronomy at Harvard University, Professor Sean Coe, Professor of Physics at Durham University, and Professor John Peacock, Professor of Cosmology at Edinburgh. Can I now first invite Professor Eisenstein to the stage?
Let's see, how are we doing this? Going to be are we okay? There we are. All right. Well, it is a really great pleasure to have been here this week and to have had the chance to meet many new people. But I have to say that I think this is the most important audience of the week for us, and I'm very glad that you were all able to take the time to come out and hear about what we've been doing. I'm going to tell you just very briefly about some of the big ideas that I work on in our field, and then I'm actually going to spend a fair bit of time trying to tell you about how we do it, and then I'll tell you a bit about myself and about my path through science. So let me just start with the idea of the hot Big Bang. So the Big Bang model, the idea is that the universe begins smooth and hot and dense. And as it cools down and expands, it also becomes lumpier. And one thing to know is that this model has been extremely successful. We can specify only a relatively small number of quantities and use ideas from our laboratory physics, the physics that we explore here on Earth. And from that, we think we can understand cosmology from a time about 1 second after the Big Bang until today. So it's really a remarkable achievement of modern science to be able to explore the universe over such gigantic ranges. One of the important things about the universe are, of course, galaxies. And the thing that we study is the clustering of galaxies. So galaxies are not scattered randomly in space. They arrange themselves into dense regions, into filaments, and into voids, places where there aren't very many galaxies. And remarkably, the properties of these maps, the large-scale overdensities and underdensities in these maps, are actually not only telling us about the universe today, but they're actually telling us about the early universe. And our work tries to use these maps to learn about the composition and history of the universe. One of the really great discoveries in the last 20 years is this idea that the expansion of the universe is actually accelerating. And this is, in some ways, a ridiculous idea. Gravity should be pulling things together. If I throw a ball up in the air, it should come down and hit me on the head. That's what you expect to have happen. Instead, what we find in cosmology is that on the very largest scales, the universe is actually accelerating away. So if I throw the ball up, it actually accelerates up and keeps going. Somehow repulsive gravity. And we call the cause of this dark energy, which is some unknown energy filling space. And what's amazing is that this dark energy is actually twice as important in the universe today as all the rest of the matter, all the normal matter, all the dark matter. So it's very important. The way we explore dark energy is by measuring the expansion history of the universe, and we can do this by measuring very precise measurements of distance. So if I have a universe, this blue line would be a universe, this is the size of the universe versus time. So this blue line is a decelerating universe. Things are getting slower over time. And the red line is an accelerating universe where it's starting to kick up over here. And the accelerating universe has more time to get back to a given size, so more distance to get back to a given size. Now, the issue is that measuring distance is actually very hard in astronomy. When you look at a star or a galaxy, you don't know if it's a very luminous star or galaxy far away or a less luminous one nearby. It's very hard to get that intrinsic sense of size. So it's a very challenging problem, a very long-standing problem. And what we do in my work is use this idea of the baryon acoustic oscillations. Okay, that's a very fancy word. And what it refers to is sound waves that propagate in the first only 400,000 years after the Big Bang. So, first tiny fraction of the age of the universe. And they propagate, and these sound waves create a distinctive feature in the clustering of the galaxies. And the feature is relatively simple to understand. If I have a galaxy here, I am slightly more likely to have a second galaxy 500 million light years away, more likely to have 500 million light years away than 400 or 600. So there's this extra little bit of clustering at those scales. Well, if I think that there's some clustering pattern, and I can see that same pattern here and here and here, then by measuring the change in angular size, I can infer the distance. So that's like if I tell you that I'm 2 meters tall, then just by pulling out something to measure angle, you can figure out how far away you are from me. So that's what we do. Okay, the way that we do it is by measuring large surveys of galaxies. And this is technologically very challenging. The largest maps use about 1 million galaxies. And I'm involved with something called the Sloan Digital Sky Survey. It's the world's largest such survey. We use a dedicated telescope in the mountains of New Mexico in the United States The project actually started in 1990, so a very long time ago. It had to build the telescope and develop all the instrumentation. So we started taking data in 1998. That's about the time I joined the project. In 1990, I was about your age, so these things take a while. But we're still running now, and we expect to run for the next few years at least. So this is the world's largest compilation of astronomical spectroscopy. Spectroscopy means taking the light of an astronomical object and splitting it up into its component frequencies, like taking a prism and measuring how much red light, blue light, green light there is. So we've done about 4 million objects. Now, one thing to know about the SDSS, and likewise with the 2-degree field galaxy survey that Professors Cole and Peacock will tell you about next, is that these are big collaborations and very enjoyable collaborations. So a lot of times one has the impression in science that scientists are individuals, solitary people. They go and they do their own work, and everybody never talks to each other. This is very much not the case in astronomy. We have a really wonderful collaboration, hundreds of scientists involved, many different interests, many different skills, many different backgrounds, and it's really the mix of all these things blended together that makes these projects successful. Okay, so this is our telescope in New Mexico. You can see that it's ready to do its night observing. It's an unusual telescope. It has a very wide field of view, and it's also unusual because it doesn't sit in a dome. So normally you think of telescopes as sitting in domes. The domes are very important. It keeps the wind off the telescope. In this case, the thing that's keeping the wind off the telescope is this shield, which is actually not connected to the telescope. It just sits around the telescope and always moves where the telescope moves to keep the wind off. With this telescope, we've imaged about 1/3 of the sky, beautiful images. These are all digital, taken in 5 different colors to blend together. Here's a beautiful picture of the Whirlpool galaxy. Here's a nice colliding set of galaxies. So just images of the sky. But these give us 2-dimensional images. We want to make 3-dimensional images. And we do this with spectroscopy with plug plates. So basically, I brought one. So this is one of the plug plates from the survey. We've done about 6,000 of these. And the location of every hole is the location where the light from a galaxy or distant quasar or star will fall. So basically, if you coated this plate with photographic film, then the telescope would make an image of the sky, of some little part of the sky, on the plate. And instead, we drill holes where where the light from an interesting object is going to fall, and into that hole we plug a fiber optic cable. So these are all plugged by hand. So people plug them. And when we expose this to the sky, then the light from the astronomical object is going to come down through the fiber and run off to the instrument. So this is the way that we can observe large pieces of the sky. So I want to pass this around the room so that you can see it. It is very heavy. You cannot hurt it. I promise you will not hurt it, so touch it any way you want. But you will hurt the head of the person in front of you if you drop it on them. So please be gentle just of the people near you, but you don't need to be worried about being gentle with the plate. And I'm happy at the end, great. I'm happy at the end to tell you more about it with the details of it. It's actually a very precise engineering thing. So this is just to show you a bit about how the plates are made. They're actually drilled at the University of Washington. And these plates allow us to observe 1,000 objects at a time over a very wide field of view. So when you look at that plate, you should think that the telescope is taking the light. Okay, we're going to have a little bit of noise here, but the telescope is taking the light from distant objects. It's actually, when it looks at the sky, it's actually taking the light from only 1/100 billionth of the sky. So it's separating out all the rest of the sky, only taking the part from only 1/100 billionth of the sky, and it's bringing that light onto that optical fiber. And in that little part of the sky, we have arranged to have a galaxy. That galaxy has light that is 1 million times fainter than what you can see with your naked eye at a dark site. So very, very tiny amounts of light. We then take that light, split it up into 1,000 different wavelength channels. So we're like splitting it up, taking a prism and splitting it up into 1,000 different colors of the rainbow. And from each of those in each of those little wavelengths will record a few hundred quanta of light, a few hundred photons, so a tiny amount of light from that, but that's enough for us to figure out how far away the galaxy is. And we repeat that night after night, object after object. We're now up to about 4 million such objects. So this is just telling you some about how the plates work. I think I'll actually skip through to the next movie here, just to give you a sense. So these then get travel down to the telescope. This is at Apache Point Observatory in the mountains above El Paso, and this is where the telescope lives, in a shed. These are the plates. They're getting wheeled out to the telescope. Telescope's being unveiled now. So this is the underside of the telescope. We actually have to tip it up. The plate will be brought in here. So the previous plate gets lowered down, the next plate gets brought up, and then this cart is going to have to get put back. These plates, when they're in their sort of full housing, they weigh about 300 pounds, so about 150 kilograms. So we need to have special machinery to move them around. This is the telescope getting ready for a night's observing. You can see the protective shed, that holds it in the day has been slid off, so the telescope's ready to try to observe. And we're staring at a particular spot on the sky now. This is obviously sped up by a lot, but to even get through a night, we'll stare at one spot on the sky for about an hour, recording the light. That's how long we have to, when in an hour we're only getting a few hundred photons in each of our wavelength channels, so you really have to be patient here. Okay, these videos are on YouTube if you're interested in them. You can also find them at the website of the project, www.sdss.org. Okay, so now just a little bit about myself. I'm very lucky that my parents are here. My parents are academics, so I got my start rather young. This is at my dad's blackboard. You can see the equations there. I was not ready for equations yet. But I think that, I'll be very brief about this, but just to highlight, it's very important when you're young to be training, to be practicing, and thinking about what you want to be doing. I've been lucky in my life to have wonderful teachers. This is David Spergel, who actually won the Shaw Prize in 2010. This is my undergraduate thesis advisor. So I was very lucky to have wonderful instructors and mentors through my career. I've also been very lucky to have wonderful friends as colleagues. These are some of my friends when I was a postdoc. I'll particularly recognize Wayne Hu and Max Tegmark as some of the two of the postdocs, my colleagues at this institution where I did my first work. They were my collaborator, my co-authors for my first papers on baryon acoustic oscillations. But really, I just want to impress upon you how important it is as you grow up through science that it is very much a social endeavor, and that one's friends and colleagues are extremely important. And of course, now I'm very lucky that I have my own family. My wife, Annalisa, and 2 sons, and the quest for astronomical knowledge never ends. So thank you very much for your time here. I really will be happy to meet any of you at the end, and I'll be looking forward to all of your questions. Thank you.
Thank you for sharing your inspiring ideas with us, Professor Eisenstein. Now, may I invite Professor Klone to share with us your ideas and work? Professor Klone, please.
Okay, well, again, thank you very much for coming along. It's a real pleasure to come and talk to you about some of the science that I've been interested in throughout my life, and some that led to the Shaw Prize. So my scientific interests are what gave rise to the structure that came out of the Big Bang, not only galaxies like the Milky Way that we live in, but the large-scale structure that Daniel described, the fact that galaxies are not randomly distributed in the sky, but form an interesting web of clusters and filaments of galaxies. and what it is we can learn about the properties of the universe from studying these things. So the model that we work on is sketched out here. It sounds quite complicated. It involves quantum fluctuations and inflation and how this evolves over time. But what makes this a tractable and interesting problem, a fruitful problem to work on, is that the initial conditions are very well specified in this model of the evolution of structure in the universe, and only depend on a few parameters, the fraction of dark matter in the universe, the fraction of normal baryonic matter, and this dark energy that Daniel mentioned. So it's a very tractable problem. You can code up the equations describing the physics of that on a supercomputer, and here you see a section of the universe evolving from those small quantum fluctuations early on under the influence of gravity, and you see structure beginning to form, first on small scales, and then that merge together to form larger scales, and eventually ending up with this beautiful complex web. Over here shows a pictorial representation of that hierarchical structure formation, whereby small things form at the top of the tree and merge together, form larger and larger halos. And it's that large-scale structure that we studied with the 2DF Galaxy Redshift Survey. Rather like the Sloan survey, we surveyed so we're looking out from the Milky Way galaxy. We're situated somewhere near the edge. We looked out in two big slices, and we measured the positions to galaxies. I think John will show you a bit more, so Professor Peacock, about how we actually achieved that with the 2DF instrument. And we mapped out the distribution of galaxies in these two big slices. It's intrinsically beautiful. There's this picture that shows one slice twisting around here. You see this real three-dimensional structure, and these walls and filaments and voids that were mentioned earlier. So by measuring the clustering as a function of scale, we're able to quantitatively learn something about the structure of the early universe. You need to go through quite a bit of mathematics to follow that in detail, but basically by measuring the clustering as a function of scale and fitting it to different models, you can work out what the fraction of matter is in the universe, what the fraction of normal atoms that make up the universe, and even combining with other data, the amount of dark energy in the universe. And we've come to this surprising conclusion, somewhere here, that I can't quite see, that 70% or more of the energy in the universe is in the form of dark energy, and of the normal material that we're made of, it is only 4%, and that's outnumbered by more than a factor of 5 by dark matter. So one can study the very large-scale structure to learn about those cosmological implications, and I think that's what we were mainly being honored for in the Shaw Prize. But one can also look at what it tells you about more the details of galaxy formation. And there, one of the things we can look at is how different types of galaxies are clustered differently. This again shows the data from the 2DF Galaxy Redshift Survey. So each dot on there is the location of a galaxy. We're looking back hundreds of millions of light years. There are 250,000 galaxies plotted in total in the 2DF survey. These are just the galaxies that are blue, that have young star-forming populations. Whereas if I contrast that with the galaxies that are red, that have ceased forming stars, they trace out the same large-scale structure, but they're more concentrated in the densest knots. And these correlations between the properties of the galaxies and their environment is something that I'm very interested in, because it can tell you something about the formation histories of galaxies. And one thing else, we're interested in not just how much dark matter there is in the universe, but what is that dark matter? And one thing I've been looking at more recently is the small-scale structure in the universe, by which I mean the properties of distribution around individual galaxies. And this shows a galaxy And the faint extensions either side are diffuse light in sort of shells and filaments, shells and plumes around the galaxy. And we try and understand how this happened. And we think it's a direct fossil remnant of the hierarchical way in which those galaxies formed. So this is a zoom in of the sort of simulation I showed earlier, showing the formation of an individual dark matter halo. We're not seeing the dark matter here. We've put in a model for where we think the stars form, and you're seeing the stars that start off at the centers of these dark matter halos falling in and merging and building a complicated structure. So the galaxy that we would normally observe is just this stuff down at the center, but from the history of this hierarchical merging, you see structure extending much further out. You see these plumes and shells. I think, yes, the interesting merger is just about to happen. So as time goes on, the fragments that are merging are larger and larger, and they produce more interesting shells of stars. And so by looking at the stars at the final time, we can flick there rapidly, I hope. Oh, not there. Oh, doesn't want to do it for me. Should have just left it running. That's the very end, yes. One more try. Since double-clicking works, maybe that works. All right, there we go. So at the very end of the simulation, one sees structure that very much looks like that initial galaxy that I showed you with these shells. And that's a fossil record of the hierarchical merging and is telling us something about that hierarchy and the structure of the halos that merged. So that's to do with the origins of the universe. I think we're also supposed to talk about our origins, my personal origins, and our walk through science. So John and I have come about a third of the way around the world from, I can't even see England now, so from this small island over here, blown up here. I work for the last 23 years in the northeast of England, over here, but I grew up not far away in the northwest of England, over this side, in a place that's almost entirely unlike Hong Kong. These two circles are the same size. I'm told that the average population density on the land inside this circle is about almost 7,000 people per square kilometre. Where I grew up, the population density inside this circle was 3 people per square kilometre. You're much more likely to see animals like cows than people. It did mean that, unlike Hong Kong, the night skies were very dark. Unfortunately, perhaps you'll guess from the nice green trees and hills, the night skies were normally very cloudy as well. But on the rare occasions that you could see the night sky, I was fascinated by the stars and the vision of the Milky Way from a very early age. I was born in 1963, and at this age, I was growing up with the space race, the Apollo space launches, and also a lot of science fiction on television. And it was this mix of things that got me very interested in space and physics from an early age. I'd never had any intentions of being a professional scientist, but I just wanted to know more about space and about the stars we could see in the night sky, as well as the distant planets visited by Star Trek. So where I grew up was a very small village. This is the main shopping street in Chipping. And I went to a village school there, and at the age of 12, then I had to travel about 10 miles to a local grammar school. And there we were notorious for being late to school because often we would get stuck behind herds of cows walking along the road to be milked. It was at that school that I found that I had an aptitude for science and for physics and mathematics, and my teachers put me forward to applying to Cambridge University, where they wanted me to go to Cambridge. I actually switched and was the first from my school for quite a long time to opt to go to Oxford instead. And the reason I did was that in their undergraduate course, in the physics course, you could do some astronomy courses from the beginning. And again, I had no intention of being a professional astronomer. I assumed that, like my father, I'd work in industry. That was the way to earn money. But I was interested in learning about planets and the stars and so on. And I thought this was my chance to at least learn some astronomy before I went to work. Back in those days, there was no tuition fees. It was my education at university was completely free. So at the end, I did very well at university, and I had the opportunity to go and study at Cambridge and carry on studying. And again, I still didn't have plans to be a professional scientist. I just wanted to learn more. And I went and did a one-year course. I was then at Clare College, that can be seen here, studying more maths and physics. And then I went on to do a PhD in Cambridge with my supervisors, Nick Kaiser and Georgia Stathiou. And of course, it's the wonderful supervisors and people who encourage you through science that guide you in a career. So from there, I went to Berkeley in California, just across the bay from San Francisco, so somewhere over here. And I was there for 2 years. And even at that stage, this opportunity to go to California had come up, and an opportunity to carry on and being paid to do science. It was really only towards the end of my time there that I began to think, well, perhaps there is a career in this, and I should apply to carry on working in astronomy. And at a similar stage, I met my wife, who's too shy to be in the audience, who's looking around the museum. And we have 2 children who are also looking around the museum at the same time. So we met just before I went to Berkeley, but we married when I moved to Durham in 1991. I'm also a keen cyclist. So I moved to Durham in 1991, and that's really where working in the 2DF project started. So we had a very small group in Durham at that time. It has grown by a very large amount while I've been in Durham, from 2 or 3 people working in cosmology to now over 20. And Carlos Frank here is the leader of that group. So in 1994, the 2DF collaboration was formed. It was a 30-strong team, so much smaller than Sloan, but still an international team, a very strong collaboration between Australia and the United Kingdom. The telescope we used was in Australia. The observations that I think John will tell you a bit more about were taken between 1995 and 2002, and it was a wonderful collaboration to be in. I was here working in Durham, and we were visiting Oxford, Cambridge, Edinburgh, and so on, where the other UK collaborators were. So I imagine many of you don't know where Durham is, don't think you've never heard of it. This is Durham Cathedral, the tallest building in Durham. It's almost 1,000 years old, and it dominates the skyline. You might think you've never seen that before. This is the cloisters, a quadrangle in the middle of the cathedral. But I suspect when I show you the next picture, I suspect many of you will realize you have seen it before. So the first Harry Potter film was filmed in Durham. This end of Hogwarts School is Durham Cathedral, but with a few augmentations. It's the 2 towers at the end of the cathedral. And so a lot of people actually know Durham, even though they don't think they do. So I look forward to answering questions later. Thank you.
Thank you very much, Professor Cole. Our next presentation is by Professor Peacock. Professor Peacock, may we have your presentation, please?
Hello. I suspected in advance that Daniel and Sean would steal all the best scientific lines, so what else can I say? So I'm going to try and come at this a little differently and talk about an individual scientific journey, how one comes to be a researcher, and how cosmology and I have evolved in parallel. So my life trajectory is pretty simple. I've moved north. I was born in the south of England, lived in a couple of towns. From the age of 18 to 24, I studied in Cambridge University. I went to Edinburgh, intending to stay for a couple of years, and I'm still there. I'm glad to live in Edinburgh because at least half my genes are Scottish. Here's a picture of my great-grandfather on his farm in 1899 in the borderlands of Scotland. And in a way, one's fascination with old photographs like this, it's the same fascination that leads you to do research in cosmology. I look at him and I think, this is where I came from. And the galaxy maps that we've been looking at and studying this research, in the same way, the key to the origin of everything that's around us today. So it's the same basic impulse, I think, that gives us a fascination with both. So let's skip over the first 18 years. In 1974, I arrived to study at Jesus College in Cambridge. By this age, already many formative events have taken place. I think for me, looking back, the most important thing was that I studied a lot of maths, and I studied it quite early. In those days, the school system was set up so that people who showed aptitude at mathematics in particular were encouraged to take additional qualifications. So right from the age of 15, I was doing twice as much as normal. That's impossible in the British system today. You can do additional maths, it kicks in later on. And one thing I've seen consistently in my career is that mathematics is the key to everything in science. It's a very sad situation. As an educator, you encounter students who are extremely keen in astronomy and want to progress in the subject, but their mathematical foundation isn't sufficient, and they struggle. And there's no substitute for learning this material early. When you're a young person, you soak up mathematics like a sponge. Even by the time you get to 20, already it's harder to take on new mathematics. At my age, alas, it's particularly hard. So one lesson that I'm glad I learned is that early mathematics is good. Another lesson at school was that teachers can be great influences. This can be for good and for bad. I had an energetic, charismatic chemistry teacher. And I was very keen on chemistry, very interested in it. I still am. My physics teacher was an old cynic who didn't care about the students. I found physics very easy, but I didn't have the enthusiasm for it. So I went to university intending to study chemistry. Fortunately, Cambridge refuses to let you specialize. It has a syllabus called Natural Sciences. So for the first year, I had to study twice as hard, do physics and chemistry. By the end of this, I realized doing chemistry would have been a big mistake because physics was so much easier. So I shifted. Like Sean, at this stage, I had no knowledge that it was possible to be a professional astronomer. I finished my physics degree. I thought, now I have to get a job. The jobs available were, let us say, building radar for the military. I didn't like that. I thought, I conclude I don't know what I want to do. I should do something to wait until I realize what I want to do. A PhD is the obvious step, a research degree, but what to do? Most of the topics on offer in physics were very narrow and specialized. Only astronomy seemed to use much of the knowledge that you'd gathered. So I did astronomy, of course I was interested in astronomy, but everybody on the planet is interested in astronomy. But I did it purely by elimination. Interestingly, Sean made this point as well. The whole journey through this was provided by the state, completely free of charge. Talented children, whatever their parental background, would be given an elite education right to the limits of what they were capable of. In Britain, this system no longer exists. I have to say, I feel that's a great shame. So I decided to do a PhD, but what area of astronomy to work in? Well, I chose cosmology. Why? There were no lectures in cosmology in those days because very little was known. Everything you've heard about in these talks has been brought into being over the last few decades pretty well. Only a small number of things were known, one of which was this equation. I don't need to say anything about the details of it except that it's short and that it's an equation that describes the change in size of the universe with time. And it's the same equation that is obeyed by something that falls in the Earth's gravity. If I let go of this laser pointer, it would fall obeying this equation. When I realized that, it blew me away. The idea that I could write down a simple equation that the whole universe had to obey, it's the ultimate in megalomania, and one never quite recovers from that experience. So I thought, I must know more about this. To do cosmology in Cambridge in those days, you had to make a choice between warring factions. There had historically been two groups, Martin Ryle's group and Fred Hoyle, both great scientists. Hoyle had a special theory of the universe called the steady state theory, in which the universe expanded, but nevertheless the matter density didn't change. So it was an eternal universe that existed forever. Ryle believed in the more conventional theory of an expanding Big Bang. This debate rolled on. The way it was settled observationally was using radio astronomy, which is what Ryle's group did. So here was one of Ryle's radio telescopes. When it looked at a galaxy, you can see the starlight here, what you found were relativistic jets of plasma emanating from the center of the galaxy, powered by supermassive black holes of perhaps a billion solar masses. These telescopes could count these galaxies and find that these massive black holes were rarer far away. So the universe was evolving. So this is the sort of thing they did, and I was lined up to do it. And indeed, I measured this evolution more precisely. So in 1981, I had a doctorate in counting radio galaxies. I also had a girlfriend, Heather, who subsequently became my wife. So here I am with a PhD, and after you get your PhD, you need a job. So to get a job, you need talent, one presumes, but you also need luck. My PhD supervisor at this stage got a new job. He became director of the Royal Observatory in Edinburgh. And here it is. I think it's one of the most beautiful working environments in the world. It sits on top of a hill overlooking the ancient city of Edinburgh, the sea, extinct volcanoes. This is why I've never left. Every time I've been offered a job elsewhere, I looked at this view and I thought, I can't bear to tear myself away. So shortly after arriving in Edinburgh, Heather and I got married. We went on to have 3 wonderful children and a dog. In Edinburgh, I've also managed to pursue not just science, but also hobbies. I play the clarinet. I play it in large symphony orchestras. I play it in small chamber groups. If you're interested, you can find us on YouTube. I should also say that I'm able to do this, again, because of enlightened state provision in education. My parents had no history of classical music in the family. I don't think it would have occurred to them to pay for music lessons, but all this was provided for free by the school. Again, this enlightened system is under threat, so I feel doubly fortunate to have gone through the system at the time I did. The other good thing I should say about living in Scotland is it has mountains. Here's a picture of my son, who I like to go climbing with, on the most remote mountain in Scotland, a day's walk from the nearest road. So it's a country that has everything apart from skyscrapers. All right, back to the science then. Arriving in Edinburgh, I discovered that the new institute had a history of survey astronomy, particularly in those days surveying the sky with photographic plates. So one could have a picture like this, where this slightly fluctuating pattern of light here represents the positions of hundreds of millions of galaxies. You also see this, which is the plane of the Milky Way. So our own Milky Way, which I know because of the light conditions here, perhaps many of you have never seen locally. It's a great shame. We live in a flattened disk, which is a system of 100 billion stars, and beyond it, there are individual galaxies like the Milky Way in all directions. But in the optical light, we have difficulty cataloguing them because the stars of the Milky Way get in the way. So I realized I knew something useful that the people in Edinburgh didn't know, which is that radio galaxies didn't suffer from this. If you survey the sky in the radio wavelengths, you don't suffer from these problems of dealing with galaxies. So at this time, I was starting to learn other new things. Particularly, if you're studying the distribution of galaxies, you need mathematical tools to do it. So one's looking at a density of material, light, that changes up and down as you march through the universe along some direction. And that's a kind of noise. And noise is something we're all familiar with. If you have a bad telephone connection, you have trouble making out the signal, which is somebody speaking to you. But the distribution of galaxies in the universe is actually a noise and a signal at the same time. These fluctuations have information, and that's why we do these galaxy surveys, to pick this out. And a lot of these tools are already in place. And one of the ways you can make progress in science is picking up techniques that were developed in one field for one purpose and transplanting them elsewhere. So I started to read books and papers about the mathematics of noise. In the 1980s, I started to write papers about applying this to cosmology. And by the beginning of the 1990s, I was writing papers applying these techniques to the distribution of radio galaxies in space and measuring how the density of matter fluctuated up and down. So I had a background that prepared me both mathematically and practically in terms of survey analysis for when the 2DF Galaxy Redshift Survey was created. So just to recapitulate, redshift surveys give us a three-dimensional picture of the universe because the universe is expanding. The galaxies separate with time. The further apart they are, the faster the velocity of separation. That's according to Hubble's law. V is proportional to the distance between them, h being Hubble's constant. So that means if you can measure this velocity v, you know the distance, and therefore build up a three-dimensional picture. And these velocities come from spectroscopy. Receding galaxies, the light is all shifted to longer wavelengths, stretched out by the velocity. So all we have to do is spectroscopy of a lot of galaxies, and Daniel and Sean showed you some of the technology by which that's done. The 2DF project used this machine, the 4-meter angular Australian telescope, where the mirror is here. Light would come from infinity, bounce off the mirror, up to this focus here, where the instrument analyzes it. So here is a picture of the instrument for which I can take 0 credit, and something that should be said very clearly is all of the three of us here today are consumers of astronomical technology. Teams of talented engineers labor for many years to make these machines work, and we all reap the rewards. So in this case, what the machine is able to do here is a plate where fiber optics, as with the Sloan Digital Sky Survey, will carry off light to be analyzed. But those fiber optics are placed not by hand in pre-drilled holes. They're put in place by this machine here, which is a robot that moves up and down across the plate until the fiber is in the right position. So we recycle our metal. That's why I wasn't able to bring you a 2DF today, because it's a metal cylinder rather taller than I am. And so here is the survey that we carried out over a period of time around the turn of the century with this machine. And I never tire of looking at this, realizing that there are these chains of galaxies which are so long that a good fraction of 1 billion years would have to elapse for light to travel from one end to the other. And we sit at the center of this pattern. We're on one of these hundreds of thousands of dots that make up this pattern. And so, as has been explained, mapping this gives us information that leads right back to the earliest stages of cosmology that set these patterns in creation. And we believe, although it's not yet proved, that this is all traceable to quantum fluctuations, that everything you see here, billions of light years, was once smaller than an individual atomic nucleus, and therefore subject to the principles of quantum mechanics, the same physics that makes the atom work. Astonishing to think that there can be a link from things so small to all of this. So let me tell you in closing a few more specifics about one particular piece of research that hasn't been mentioned yet, which is the so-called redshift space distortions. And these arise very simply. You've seen, this is a still from the kind of numerical simulation that Sean showed, where one puts representations of small density fluctuations into a computer, lets gravity act to pull material together. Well, you can't make an omelette without breaking eggs, in the old saying. In this case, you can't congregate material together into high density regions without pulling it from somewhere else. In the old saying, the rich get richer. So look at this. Oh, that's interesting. Ah, dear. There should have been several of these. Never mind. I've lost a couple of slides, so I want you to imagine there's material here. Everything is more or less uniform. So in order to move from here to here, it has to have a velocity. So associated with these density contrasts is material moving in. The question is, can one measure that speed? And the answer is you can, because it influences Hubble's law. Hubble's law says the velocity is proportional to the distance. But that's true in a uniformly expanding universe. As soon as we introduce inhomogeneities, these additional velocities mess up the velocity from what it should be. So your distance is no longer precise. So therefore, here's a simulation of the 2DF survey as it would be if we could measure precise radial distances. Here we are, here is every galaxy a certain number of meters away. That's what we call real space. Now let's go to redshift space, where we add in what we will really see, the effects of the peculiar velocities. So you can see this has a number of subtle effects. Supercluster, this chain of things, hundreds of millions of light years across here, all appears to move. Also, dense knots of objects are stretched out along the line of sight. So there's a great distortion of the picture here, which seems unfortunate, but is also very fortunate because it allows us to measure this signature statistically and therefore figure out how fast the matter is flowing into superclusters. And since these velocities are driven by gravity, it should be obvious to you without any technical knowledge that the more mass there is in the universe, the higher its density, the higher these velocities will be. So this signature that we measured directly in the real data was one way in which the density of the universe could be inferred. So this was a contribution to this picture, which we call the peculiar universe, that only a few percent of the overall energy density content of the universe is in the form of ordinary atomic material that makes up this desk, my head, or the air around us. The total matter density that we can weigh using redshift space distortions comes out to be about 6 times as high as the density of ordinary material. So this is the evidence for the so-called dark matter, matter that we detect only by its gravity and whose nature is as yet unknown. However, the other part of the story that you've heard told already is that the majority of the universe is actually in a form of matter that doesn't clump, the so-called dark energy that spreads uniformly throughout space, effectively giving empty space itself an energy density. So the space in this room holds some dark energy. We'd also like to know what that is. Maybe we'll be back in a few years getting another prize and telling you the answer. But my time is up. I hope a few useful things may be learnt by people at your sort of age, contemplating perhaps a scientific career. How could this go forward? One thing is that you may worry that you don't quite know what to do, and this is normal. It takes time, I think, to learn about yourself, to understand what your capabilities are, what your interests are, and to find a way in which you can maximize both of those simultaneously. In so doing, you may be prepared, as I was, to immerse yourself in the unfamiliar. I think it's fruitful to move from areas that you're familiar with. Don't just stick to the things you know, move into something new. And at least personally, I would say, in so doing, if you become, in the end, a research scientist, if you want to be a success, I think you don't want to intend to be a success. The way to achieve success is to start with understanding. When you move into a new field, you know everybody else knows more than you. You simply try and make sense of what the greats of the past have done, and eventually you realize that they haven't done everything, and new opportunities emerge. But lastly, of course, this can prepare the way, but in the end, a successful scientific career depends on a great deal of luck. I've been lucky to be in the right place at the right time in the projects I've worked on and in the colleagues I've had, and I'm very grateful for all of that. Thank you.
Thank you very much, Professor Picon. Please take a seat here on the stage. The discussion section is about to begin. May I invite Professor Eisenstein, Professor Kroll, and Professor Young to visit on the stage too.
Can we begin this Q&A session after this very interesting presentation by the three professors? Perhaps we shouldn't say Q&A, interaction. Just talk, let's have interaction, a community, a social endeavor. So the first comment I invite from the floor. Come on, the first thing to do on the way to being a scientist is to ask questions. There is no such question as a dumb question, right?
There are plenty of dumb answers.
Yeah. Take the question over there.
唔好意思，我用中文問啦。
I'll try to translate.
OK，唔該，我想問一問咧，其實嗰個宇宙嘅結構咧，佢係本身係好似一個cheese 咁樣，即係一個窿一個窿有啲結構維持住。佢本身個結構會最後再擴大之後，會唔會即係會即係點講叫 broken 啊？叫斷咗或者叫爛咗，或者會成個結構會崩潰咗？到最後即係如果再擴，因為而家佢個宇宙嘅理論係不斷咁向外擴張噶嘛，咁佢最後會唔會全部摧毀晒咧？唔該。
Okay, well, I have to more than translate, I have to slightly reformulate. It's a question about the structure of the universe as it appears in some of those pictures. Looks like Swiss cheese. I think that's more or less the question with lots of holes. And as the universe evolves, will it break down? What will happen to it? Is that roughly what you mean? Yeah, okay.
The problem with the pictures that we showed you is that they're only two-dimensional. So you have to wonder what the three-dimensional structure that is being sliced here looks like. And actually, around the Swiss cheese, a better description is a sponge. So if you think about a sponge, it's a network of holes, and a fish can swim through the holes to reach any part of the sponge. And the structure of the sponge works around the holes. So the sponge is like an anti-sponge. So the three-dimensional structure of the universe is like this. And so when we slice through the sponge, we see bubbles, but 3 dimensions is more complicated. Now, as the universe continues to develop its structure, the scale of these features will increase, but the sponge-like nature will remain the same.
Thank you. Other questions? I have some written questions here, but I would give preference to oral questions first of all. Do I see any hands? Yes, in the back.
Hi guys, I was wondering, you said that the universe expansion rate is accelerating, but is there a time when when it will stop or even collapse on itself, the universe, I mean?
Very good question. So the answer is we don't know. The usual simplest theory would say that it will continue to accelerate, which means the universe in that sense sort of gets infinitely big. And it may be that will be what happens. But I'm cautious about this because we used to think that the universe must be decelerating. Of course, that's what gravity tells us should happen. And so we were Most of us were very surprised when we find that, okay, it was decelerating for 6 billion years, and then recently, in the last 6 billion years, it started accelerating. So this makes me nervous about predicting the future. But for now, within our theories, it accelerates, and it could be that at some very, very distant point in the future that something, catastrophically different will happen, and we don't know because we don't understand the theory. We don't really have a good understanding physically of what's causing this acceleration.
Could I pick up on that point and ask, when you started on your research when you were sort of their age, just entering university or even younger, the assumptions about the universe were quite different from those that we see today, and even the questions that people asked were quite different. So what is your advice to young people about keeping an open mind, being prepared to be surprised, and not believing everything you read in textbooks?
Well, you're right. In the preface to my PhD thesis, I wrote that throughout this we will take without question the fact that in modern terms the dark energy density is 0, because to imagine it was non-zero is clearly crazy.
That was the same mistake you made as Einstein did. So you are in good company. Okay, other questions, comments in the front here?
Can I ask that you mentioned about the cold dark matter? Is the hot dark matter have been putting out?
It used to be thought that hot dark matter was an alternative for cold dark matter. The difference between these is what the mass of the dark matter particles is. The hot ones are very light and move very fast, and the cold ones are very heavy and move very slowly. And the difference that makes to structure formation is that if they're very light, they quickly spread out and erase the small-scale structure. Whereas if they're very cold, the first things that form are very small, and then they merge on larger and larger scales. The hot dark matter picture has essentially been ruled out. The microwave background tells us the amplitude of the fluctuations on large scales, and the fact that we see quasars and structure forming at high redshift tells us that small-scale structure formed early on, and that just can't happen in a hot dark matter model. But there's still possibilities of warm dark matter, somewhere in between. And there you erase the structure on the very smallest scales, around the scale of dwarf galaxies. And that's some of the work that I'm interested in now, and one of the videos I showed you was, are there differences between warm and cold dark matter?
But just to add to that, we do know now for certain that hot dark matter exists. So in about 1980, there was a great period of excitement in cosmology because experiments done by nuclear physicists indicated the neutrino had quite a substantial rest mass. Now, one thing I think we all agree is taken completely as certain is that there is a relic background in the universe of neutrinos left over from when the universe was very hot and dense. They're with us in this room today, very hard to detect directly. But if you give those neutrinos enough of a rest mass, that can dominate the energy density of the universe. And with the 1980 measurements, that looked like this would work. But now we have direct data from experiments like Kamiokande and the Sudbury Neutrino Observatory in Canada that give us partial knowledge of the masses of neutrinos. So we know that neutrinos have some rest mass, and so that they make a contribution to the energy density of the universe. But we also know that that can't be high enough to account for what we see. But one of the future goals for cosmology is to measure precisely and directly this small hot dark matter fraction.
Could I add to that a simple remark that one of the last important parameters in this neutrino puzzle, one of the oscillation angles, was actually measured about 2 years ago in Daya Bay by a team including Hong Kong scientists, including a few who were not much older than most people in the audience. A very small mixing angle was measured from Daya Bay. Okay? I think this is an interesting question here among the written questions. Could I perhaps raise this one? Did you have the idea of baryonic acoustic oscillations in mind and then you went out and looked for the evidence, or was that a surprise to you?
So the survey itself was not designed to do baryon acoustic oscillations, but I actually joined the survey in large part because I was looking for things like this. So, and I had worked on them previously. So, you know, in a sense, it was a surprise. It wasn't what the survey was designed to do, but one of the lessons in this kind of survey world is that the data is useful for many different things, and it turned out to be very, very good for this.
Thank you. Other questions? Is there one? Here.
Recent news that the mathematician proved that the black hole does not exist. And then, how do you think this finding will change your research and also change the theory of the Big Bang?
I missed a key
Can you
word.
repeat the question, please?
I missed a key word.
Recently, a mathematician proved that black hole does not exist in mathematics. And how do you think this finding will change your research and also the theory of Big Bang?
Okay, we think the question was that it's been claimed that black holes don't exist. Does this have any consequence for the work that you do? And I would say the answer is no, with qualifications. Everything that we've described has used, implicitly at least, the relativistic theory of gravitation that dates back to Einstein in 1915, of which I would have said black holes were a consequence, but suppose you disputed that they're not a correct solution of Einstein's equations. Black holes are regions of strong gravity in which the fabric of space-time is distorted by a large factor compared to the pretty well flat space-time that exists in this room. So although you saw large density fluctuations in these maps, you know, we've imaged regions of space that are thousands of times denser than the universe on average. In terms of fluctuations of space-time, those are tiny. The fluctuations are about 1 part in 100,000. So this is what we would call weak gravitational fluctuations. It doesn't really matter at that level whether black holes exist or not.
I'm not pretty sure is my question related to science, but maybe yes. I'm just interested to know that after hearing you say that you are not supposed to go into science research at first. Some of you may be working in other fields for a couple of years and then go back college to get a master PhD. And how can you be sure that you are walking on the right track? Or maybe Mr. Eisenstein, you said you joined the survey because you are going to find something that is not supposed to do originally by that project. So how do you get your inspiration from?
Well, it's a mixture. It's one of these things where I think that if you think too many years ahead, it all seems impossible. And yet, when you're actually in it doing it, it seems reasonable. So I guess my experience going through college and subsequent training was that whenever I was in a given year in school, and looking 2 years ahead, it seems like, how would I ever be able to do this and such? It just seems so far away. And then when you actually get there, you're within a few months, you're like, oh, I'm ready to do this. So I think people one develops over time. And I found that it's sort of, okay, it maybe isn't surprising when you're in a college or high school or secondary school. Okay, you can look at the course curriculum and see, oh, I'm going to be learning something very different 2 years from now. What's maybe harder to appreciate is that period of learning doesn't stop when the courses stop. All through graduate school, all through postdocing, all through my later professional life, I'm always feeling like, I'm a much more informed person than I was 2 years previous. So the learning really continues. So I think that you need to follow the path more locally. You need to make decisions based on what you're enjoying, what you think is working, and don't worry over much about having a 20-year plan for how it's going to work. You won't recognize yourself 2 years from now.
Yes, I think you have to look both at the very nearby, that is just solving today's problem, whatever you happen to be interested in at this minute, but also look very broadly, because what you want to be aware of is opportunities that may be suitable for using your skills that are well away from where you think you're headed. When we hire people, we often ask them questions about their broader knowledge. We may have a job to hire a cosmologist, a member of staff in the university department. And sometimes we say, okay, outside of cosmology, outside of astronomy, what's the most interesting thing that you read about in science in the last year? Sometimes they can't answer. Such people don't get the job.
Perhaps I could interject a question here that's somewhat related from one of these in these pieces of paper. What are the major challenges you have encountered in your work, and how have you overcome them? Anybody want to rise to that one?
I guess I think the biggest challenge that I've felt in my work is the pressure, the rather individual-oriented pressure that one can feel in science. It's an intellectually very driven field, and but it's the job market to enter the professional ranks is competitive, and so as a result, one puts a lot of pressure on oneself to continue to perform well, and you can't let that paralyze you. You have to be able to deal with that kind of external pressure and continue to move forward and have a confidence that you're gonna be able to do well, and that can really be difficult. So I mean, of course, there's challenges in one's work, and one has to, be able to make a given computer code work, or make a given instrument work, or figure out a particular calculation. But I actually think the bigger challenge over the years is the internal pressure of being able to keep oneself focused on making progress.
Anybody else wants to comment on that
I
one?
think I would second that. Obviously, at the day-to-day level, almost everything you're concerned with is, why doesn't my computer program work? Actually, one problem is that you can get too deeply into the problems. I can think of many days where I've spent all day wrestling with some technical difficulty and give up at the end of the day, say, I've spent 10 hours on this, I'm not getting anywhere, I must be stupid. I get on my bike to go home, and the moment you release your brain from this struggle, the answer is obvious, and you realize you could have had it hours ago. That's one of the reasons I make sure I do things outside of science, like music, because it gives you this release.
Yes, I think I've echoed that. I think it's important that so there are stresses, trying to meet deadlines and trying to get code to work, and we've all spent hours debugging code. So I think it is important to be able to switch off and have something that distracts you and gives you a break from those things. Because often in the morning, the next day, the solutions appear obvious, whereas if you wore yourself out trying to find them, you just go digging a well that you get stuck in.
All right, I think we have a few more minutes. We have a couple of questions here. No?
It was exciting to see Daleks and Doctor Who from the slide during the lectures, and I would like to know, where do your inspiration come from?
I mean, I think those things did actually inspire me to try and learn more about science. But I don't think they've actually solved any physical problems for me. Now I tend to watch them and get annoyed when they get the physics wrong. But I think as John was stressing earlier, having a very sound background in mathematics is what's useful. But I talked to some of my colleagues and I asked them, when you're trying to solve a problem, how do you think about it? And a lot of them say, well, I try and formulate it in terms of the equation and so on. Whereas I think quite often I start by just trying to visualize what's going on. And I think the time I spent in undergraduate labs and so on, seeing how physical systems operate in practice was actually very useful. It gives you much more physical intuition about how a system should behave. So when you're doing the mathematics, it's easy to get a sign wrong or do something wrong with a term, and you get an answer that's completely crazy. But unless you have intuition about how it behaves, you don't know it's completely crazy, and you can waste a lot of time. So I get a lot of inspiration from just looking at things, maybe on the building site that our hotel's looking at the moment, physically what's going on, and thinking about the physics of what's involved.
Perhaps we have time for just one more question. This young man here.
Hello. So I'm sure you've all heard of antimatter. And I want to ask a question that if antimatters are basically just like matter, is it possible that there are planets out there that are made out of antimatter?
It used to be thought that there could be sort of equal amounts of matter and antimatter. We now know that's not true in terms of we know the ratio of matter to antimatter because it's important in determining nucleosynthesis in the early Big Bang. The ratio so the matter and the antimatter will mainly annihilate and produce photons, and the ratio of photons to baryons affects nucleosynthesis in the early universe. But the universe is very big, much bigger than we can see, and there are ideas of multiverse and distant universes where things are different. So on those sort of scales, there could be an antimatter universe somewhere else.
But definitely not individual astronomical objects. In the early days, when you took a picture of the sky, you would see galaxies as individual blobs widely separated, and people speculated that maybe the next galaxy over could be made of antimatter, and wondered if there's any way we could tell by analyzing the light from it, and the answer is not. But we now know and can detect gas that permeates the whole of space, so there's no separation between galaxies. So the gas around the Milky Way would meet the anti-gas that surrounds the next galaxy. There would be annihilation, there would be gamma rays. These would have been detected, so we can be certain that anywhere within the visible universe there's not significant amounts of antimatter. And so one has to seek a solution in the application of particle physics, an asymmetry between particles and antiparticles in the early universe to explain how this arose.
Well, thank you all. I think we must bring this session to a close because we have another part to this forum. And before we disperse, let us give Professor Eisenstein, Professor Peacock, Professor Cole a big hand again.
Thank you very much, professors, for sharing your views of doing science in astronomy. Please take a seat on the floor and have a rest. We will begin the second part of the forum very soon. Now, may I invite Professor Yang again to give a brief introduction on second part in life science and medicine. Professor Yang, please.
Apologies for the slight delay. There may not be antimatter in the universe, but there are Macs and Windows, which do not quite work together quite so easily. The second part of this forum will be about life science and medicine. And you all know about proteins. We are made of many protein molecules and so on. Proteins are manufactured in specific compartments inside cells and then exported to the space outside the cells. But before they come out of this compartment, which are equivalent to a protein synthesis factory, they are subject to a kind of quality control. The work being honored by the Shaw Prize in Life Science and Medicine this year is about a detective story that led to an understanding about this quality control mechanism, the unfolded protein response, or UPR. It is a fascinating story about how this complicated and delicate mechanism was elucidated. Speaking to us, in turn, will be the two laureates in life science and medicine, and they are Professor Peter Walter, Professor of Biochemistry and Biophysics at the University of California, San Francisco, followed by Professor Katsutoshi Mori, Professor of Biophysics at the Graduate School of Science, Kyoto University. Professor Walter first.
Thank you so much, especially for organizing this kind of forum. I think it's a wonderful idea to have this opportunity to share our life stories and enthusiasm. I think when I got the Shaw Prize and read the citation of the Shaw Committee, one of the most wonderful things that it said there is this is one of the most fascinating detective stories in biological sciences in the century, which I think is precisely describing what we're doing. We are detectives, we're explorers, and that's, for me, where the excitement about the scientific approach comes from. We don't just measure things, we go where nobody has gone before. And it's these moments of making discoveries and putting dots together that previously haven't connected that make it all worth, especially since most of the things we do don't work. So I grew up in Berlin, so I'm German. And as a child, I was always just curious about how things are put together. So I brought all sorts of equipment home, took it apart, tried to put it back together, and so on and so forth. So the act of discovering and seeing how things work fascinated me. My dad had a little chemist shop, and I got excited by all these chemicals and mixing them together in our apartment at home to make fireworks. So my interest in chemistry was basically playful, playing with things that nowadays I think children should not be allowed to play with. And it's from this, I think it's a playfulness that then evolved into more serious science, and I was determined when I was 12 years old I wanted to become a chemist. So I got my high school education. I went on to study chemistry in Berlin, and I took some classes at one of our research institutes, and basically they told me, since I never was very good at languages, that unless you learn some English, you're never going to make it as a scientist. So they encouraged me to go to the United States to take a 1 year, 9 months fellowship. I applied for a Fulbright fellowship to go to a place of my choice in the States, and I was rejected because my English wasn't good enough. And I then persisted, and that's one of the messages I would like to get across here, is that, again, there is no plan, and you will both succeed, but you will also fail at many different stages. And it's a matter of being persistent at going through it. So I applied for another fellowship. I got a direct exchange fellowship, and I ended up in Nashville, Tennessee, which, coming from Berlin, was an extreme culture shock. Berlin being a big city with a lot of cosmopolitan things going on, Nashville was rather backwaters and very, very strange for me. So I ended up there and I started studying organic chemistry, synthetic, making molecules, figuring out where every carbon comes from in a biosynthetic pathway of an alkaloid. And basically, in the end, I thought these questions are rather small. They're rather limited. I would much rather ask bigger questions, and that sort of caused an evolution to become eventually a biologist. So the scale is now changing, right? You've heard about light years and millions of light years. Now we are talking about nanometers and little cells that are micrometers in scale. So by chance, I met one of the trustees at Vanderbilt, who also happened to be a professor at Rockefeller University in New York, Stanford Moore, a Nobel laureate. And I don't recall why he ever spent time talking to me. I was just a lowly undergrad student, but he advised me to apply to Rockefeller University and get a PhD in biology. I applied, I visited, I went for interviews, and I was rejected. And then a couple of weeks later, and I was determined to go back to Germany. Everything was sort of perfectly set. I had my German girlfriend and everything. A couple of weeks later, I got a letter saying that I had advanced on the waiting list, and they took me as sort of the last addition to Rockefeller University. I still have my rejection letter to this day. So when you get these things, you have to keep them and then show them as slides when you give talks there. So I went to Rockefeller University. I talked to many of the professors. And the lab I really wanted to join told me that the lab was the lab of Professor Günter Blobel. He told me his lab was full and he wouldn't take any students that year. And I talked to many others, and I almost joined another lab. And it would have been a disaster because there was an absolute, as I now know, then I was very naive, as I now know, it would have been a complete personality mismatch. And again, serendipity happened. Günter, my PhD advisor, gave me a call and said, okay, why don't you come by and we try it out for a little bit. And this was probably the best thing that ever happened in my career, because finding a mentor, a person who you can actually really closely interact with and where you have a dialogue that goes back and forth, has had such an influence on my career as a scientist and as a person. So really choose carefully who you're going to work with. It's not just the science. I could have been happy doing many different things, but it is this personality and this enthusiasm, and it's a very personal match. So pay close attention to that as you go along. My PhD thesis was wonderful. We did biochemistry and sorted out basically mechanisms by which proteins in the cell end up in the right correction. And we identified the machinery that sees zip codes in proteins and brings them to the right locale. Now, why is that important? And I thought I'd show you a few slides that don't necessarily illustrate what this prize is for, but it puts things in a wonderful context. Because this is why we should all be fascinated about biology. This is what we want to understand, right? Every organism, the sea urchin, this little mouse, or this sea plant here, is derived from a single cell that then gets fertilized and divides and builds the organism as the cell develops into a multicellular community of cells that all have to interact with one another. And there's nothing better to illustrate this than just watching it. So here's a fertilized frog egg cell. It divides, and at this point the cells are still the same. You can pluck them apart, you get two frogs. But as development goes on, these cells divide, and now they have to build other different organs. They have to become different from one another. In addition, they have to know where they are. So here's the same again. Now we watch 3 eggs here doing their thing. You see this happens synchronous. There are timers built in. The cells become, as they become these multicellular organisms, you see that they will start moving around. It's reorganizing the different tissues. And all of this, in the end, has to boil down to chemistry. and obey the laws of thermodynamics and physics. So you now see that an eye developing here, the dark spots. So these cells have to know where they are, and in that position they have to change their fate, right? And eventually you get this little tadpole. This is about a 2-day movie here compressed into a minute or so. And then now they have little character here, right? They want to get out of there. Isn't that amazing? And this is basically what we want to understand in biology. So here he is, happily born. So the miracle of our bodies is yet another one, right? I mean, each of us is composed of about 10 to the 12, 10 to 13 different cells. And they are roughly of some 200 different kinds. And all of these cells live in mutual symbiosis, right? They're all there. They need to know where they are. They need to be specialized. They need to do the right thing at the right time. And if one cell, this is about 1,000 times more than we have people on the planet. If one of these cells becomes selfish and just divides wherever it wants, we have cancer, right? So it's an amazing organization, an amazing amount of fidelity that has to go into the process of building an organism as we are. All of our cells, by first principle, by approximate, have about the same amount of the same DNA. So that's the blueprint. We know that. We know the human genome sequence. And everything that I just told you, all these processes, have to be transcribed, have to be encoded in this blueprint. And our goal as biologists now is to learn how to read it and to figure out how is the information that we have in our inherited material translated into building an organism. So as cells then become, from the egg cell, they become different organella cells, they have to know where they are, they have to talk to each other, they have to become specialized, right? Your liver cell is very different than the cell on the tip of your nose. So they have to change their structure, they have to change their behavior, they have to change their cell fate. Some cells die, that's why we have gaps between our fingers, because the cells that were there in development were programmed to die in that position. So that's how the digits develop. Now in the cells, as you already heard in the introduction, we have different compartments, different organelles, right? And you see that these membranes here provide barriers that sequester components into environments that have different chemistry and that have different proteins that are being built here. And the organelle that we've been most interested in is called the endoplasmic reticulum, this complicated network of things here. And this is where all the proteins are being synthesized and put together and assembled properly that eventually end up on the outside of the cell. So they then get moved from here through different compartments and eventually are secreted or stay in the cell membrane. And these are the components which cells talk to each other, right? They are the hormones that are being secreted, or the extracellular matrix that's built in which the cells are embedded, or there are the receptors that interpret information that comes in from other cells. They have to be made of the highest quality. Otherwise, the cell becomes a cell that doesn't know how to behave properly in the context of an organism. And it's this pathway then that determines that you need to have enough of this endoplasmic reticulum compartment in order to make sure you can fold the proteins properly. And if you don't have that enough, then you start making mistakes, and that's bad. And what we've done is we've figured out the machinery that sits in the endoplasmic reticulum and that figures out whether the capacity of that organelle is large enough, and if it's not, then a signal is being sent from this organelle to the gene expression, to the DNA, the gene expression system in the nucleus of the cell, and that then makes the appropriate genes to build more of the organelle according to need. And it's an absolutely beautiful molecular pathway. We know the components on it now, and Kazu is going to tell you a little bit more about that in his talk. But you see here in development, this is what's happening. This is a cell that is just undifferentiated. It then becomes the cell that makes all the antibody molecules that float around in your blood and protect you from disease. And you see in this step of development, there's hardly any endoplasmic reticulum visible here. It now builds up into this massive structure to handle this secretory load that the cell has to encounter, right? And this is sort of a vast amplification. This is a professional secretory cell that makes its own weight every day in protein it secretes, and accordingly it amplifies the organelle that it needs to make these proteins with incredibly high fidelity. And the structure itself is beautiful. I mean, this is the endoplasmic reticulum. It's these convoluted membrane structures that sheet-like or tubules. How is this built? What are the molecules, right, that form these structures? How is it put in the correct spot in the cell? All of these are questions that are ongoing and where we would like to seek a molecular answer to the biological question of how do you build a structure. And my personal bias is always, I'm a chemist at heart still, and I would like to know what are the molecules that do this, not just descriptive cell biology, but rather figuring out the entomology and the understand proteins as little machines that make up these things. Now, when cells cannot make enough endoplasmic reticulum because they're stressed in the ER, then rather than putting the wrong protein out there or protein that's misfolded and misfunctioning, these cells are programmed to die. This is a good example here. So here are cells that are happily growing, and on this side we induce ER stress that the cell cannot deal with, so an overload of proteins, and now you see that the cells are shriveling up and dying this terrible death. So this is the protection our bodies have, right, from making sure that rogue cells that cannot fold these signaling machines properly never make it. And it's this life-death decision that our pathways make for cells that puts in the center of many different diseases. So we have instances where cells have forgotten how to die, and then we get cancerous outcomes, or we have cells that die when we would rather have them stay alive, like in type 2 diabetes, where cells just have to make too much insulin to sustain their secretory load, and they trigger this cell suicide program. So these are the kind of questions that we like to address at the molecular level of the machinery. Now, from Rockefeller University, I moved to San Francisco. At that time, other personal things influenced this kind of decisions. So my German girlfriend was no longer in the picture. Instead, I met, this, by the way, this is my lab. I met Patricia, who is my partner for the last 35 years. And it's another one of these instances that happen in life and you just can't plan for it, right? Things happen one way, and looking ahead too far doesn't always pan out in the end. And it's again, a very, very big decision that you find a partner who can stay with you throughout your career and be supportive. And Patricia has done one other thing, and that is she has been an amazing catalyst in development of myself. So as you see, as we heard before, right? I mean, looking back a few years, you don't recognize yourself. I don't quite recognize myself either. And the question to the woman in the audience is, of course, I mean, would you have dated this guy? So otherwise, I think I agree with everything that was said before. Science is incredibly a social, a communal enterprise, right? Just going back to my lab here. These are the people who've done all the experiments. They deserve all the credits. We have numerous collaborators that bring in different expertise. And it's a very, very joyful group. That said, there's one thing I take issue with, and that's what John said last, that you have to have luck. I think there's a much better word in the English language, and that's serendipity. Serendipity is a word that, because I mean, our career is not just gambling, right? Our careers, and I wouldn't advise anybody to go over to Macau and work on getting more research funds. So serendipity is a very recent word in the English language. It was introduced in the 1700s, and it's based on a fairy tale, a Far Eastern fairy tale of the three princes of Serendip. So there was a big king, and he sent his three sons down the road to discover the world. And they meet a camel driver, and the camel driver tells them, "I've lost my camel, have you seen it?" And they say, "No, we haven't seen your camel. But is it the camel that's missing a tooth, that's limping on the left leg, that's blind on the right eye, that's carrying honey on the right, that's carrying butter on the left?" And they get promptly thrown in jail because if they know so much of that camel, they surely must have stolen it. Now it turns out they've really never seen that camel. The camel is found, but they had concluded all that information from little clues that they found on the side of the road. So there were clumps of grass on the road, the size of a camel's tooth. So obviously the camel must have been chewing it, and then it was falling out where the tooth was missing. The grass on one side of the road was growing much better than the other, but was eaten where it wasn't growing so well. So the camel must have been blind on the left side. There were only 3 footsteps in the sand. There were ants attracted where the butter had dripped, and bees attracted where the honey had dripped. So they made all these conclusions, right, from little observations that at the time didn't make any sense. But once they knew a camel was missing, they put all of that together and then built a great hypothesis that allowed them to conclude this information about the camel. This is precisely the kind of detective work that we're doing every day in the lab, right? So serendipity means to discover something that you weren't looking for, that you were not in quest of, by tenacity and sagacity, so cleverness. And I think it describes much better what we do as scientists in the lab. And all of the discoveries, I would say, we've made in the lab, the real discoveries where nothing was predictable, came out of serendipitous events, and they actually happen quite often. We know so little, there's so much to learn, and there are careers for all of you in the science if you want to. So anyway, the camel is found in the end, the princes get rewarded for their cleverness, and so on and so forth. They get their princesses, and they've lived happily ever after. Thanks.
Thank you very much, Professor Walter. Now, I would like to invite Professor Mori to deliver his speech.
It's my great pleasure to be here. This slide, first slide, yesterday my lecture, titled Quality Control by the Unfold Protein Response. Just start with a brief introduction of our field. As you know, DNA is a genetic material, the molecule that carries heritable information. And DNA contains information how amino acids are connected to make proteins. Then this information is transcribed to the RNA, and the RNA is translated to produce protein. But protein, when synthesized, are linear polypeptides. It's just like a string. But we are living in a 3-dimensional world, so string cannot do its job. It must be folded. It must have correct tertiary structures to fulfill the function assigned by genetic code. For example, insulin is a linear polypeptide when synthesized, but it must have this type of beautiful structure via protein folding to bind its receptor. If insulin binds receptor appropriately, this receptor sends signal to lower the blood glucose level. Okay? Then human can be healthy. But insulin cannot be folded properly. This misfolded insulin cannot bind to the receptor. That means such person cannot decrease the blood glucose level. Then if such a situation continues, such a man get diabetes. This protein folding is very important in your health. About 20 years ago, well, maybe 30 years ago, protein folding is considered to be very easy things. But it turned out to be, it's very difficult inside the cell. Because inside the cell, protein is very, very crowded. Many proteins exist. Okay? Especially, protein has, amino acids are classified into two classes. One is hydrophobic, amino acid like water. The other is hydrophobic amino acid. It hates water. Then this hydrophobic amino acid is in high concentration. It makes inappropriate interaction, makes protein misfolded or even aggregated. So inside a cell, protein folding is very difficult. So it's a quite serious problem. So how we can deal with this? Scientists in 1980s try to answer the question. Then they find our cell contained special type of proteins called molecular chaperones. This chaperone helps folding the proteins. Okay? So many types of chaperone exist, but most principal one is this molecular chaperone binds this hydrophobic amino acid to avoid inappropriate interaction, then help protein to be folded. Then this is the unfolded protein response Peter already told, which by researching this UPR, Peter and I are awarded to the Shaw Prize. How I met this unfolded protein response. It's quite interesting thing. So I'll just start my own life. When I was born 1958 in a small town facing Seto Inland Sea in Japan. It was my childhood dream to be a PhD scientist because I love to read comics. These are Mighty Atoms in Japanese and in Astro Boy in American movies. I love to read many this kind of comics, and I found a bright future in science technology. So I wanted to be a PhD scientist. But although my family was not rich, my parents here worked hard, allowed me to go to school. As rich as I wished to, this dream came true. I really appreciate them. Then, I also like to read newspapers. I lived in a very small town, so most of my knowledge in science came from newspaper articles. When junior high student, newspaper describes new discovery in the particle physics, discovery of new quarks called up and down. Then I was amazed by the fact. I know atoms consist of nucleus and electron. Nucleus consists of proton and neutron. Still, more smaller guys exist. How many quarks there? And how small material can be divided? That's my first question. Then later I realized that my third year in junior high school, Dr. Masukawa and Dr. Kobayashi predicted total 6 quarks. And their prediction was right. They got Nobel Prize 2008. So during this time, I knew particle physics, and I knew first Japanese Nobel laureate, Dr. Yukawa and Dr. Tomonaga, graduate from Faculty of Science, Kyoto University. So, I want to go to Kyoto University to enter the Faculty of Science to particle physics. That was my first dream. Then in high school, so I studied hard to enter Kyoto University. At that time, I didn't like biology at all. Textbooks seemed very descriptive, and I felt like I had to learn everything by heart. There are no basic rules compared with physics or chemistry. So I keep working on physics or chemistry. But at the third year, I lost confidence to enter the pass examination to Kyoto University Faculty of Science, because it's quite difficult. I did not want to fail the entrance examination, so I took easy way. So I changed my direction to chemistry. Chemistry is a little bit easier than the physics at that time. So, chemistry is more interesting to me than biology. Then entered the Department of Chemistry. As a freshman of Kyoto University, still most of my learning came from newspapers. Then this year, newspaper suddenly described a work by Dr. Susumu Tonegawa. It's the first Nobel laureate, Japanese laureate in medicine or physiology. The newspaper described the result of molecular biology. Then I was amazed by the fact that this genetic code is conserved from E. coli to human. Oh, biology has a basic rule, not descriptive. Then this rule allows science to produce human protein in the E. coli. That's very productive, and it's help people, because insulin used to be a very expensive drug, because insulin must be extracted from a dead human body. But if human insulin gene was introduced in the E. coli now start to synthesize human insulin. So my father suffered from diabetes, but now he is a retired man, but he can inject insulin every after meal because of this genetic engineering. So I fascinated with this biology, and then I decided to change direction to chemistry to biology. I looked for the department who accepted me, but fortunately, Department of Pharmaceutical Sciences accepted me. So I became closer to the molecular biology, but still, it's a long and winding way until really start to molecular biology. It took 12 years, because no molecular biology programs were operating in my school, so I chose biochemistry. But research was very interesting. Entrance examination, we have to answer questions which have only one answer. But in the research, we are trying to answer a question which has no answer. That's very interesting. So I wanted to be a PhD science, and I want to stay on academia. Then at that time, Japan had no postdoc system. My senior in the laboratory was almost all went to the pharmaceutical companies. So if you want to stay in academia, many PhD scientists in Japan at that time waiting for opening of the academic position by doing a part-time jobs. So I didn't want to do such a thing, but very fortunately, associate professor in my laboratory became a full professor in the local university, and he recruited me to the university. So I got a permanent position at the local university. And I worked hard, but it's a biochemistry project. I worked hard, but I could not enjoy that job. So I don't think this is no promising for my future. So I decided to quit the job and go to United States to learn molecular biology. Then it's quite challenging. People around me were worried about so much, but it seemed too challenging. But fortunately, I took a risk because I wanted to do something more interesting and important. Very fortunately, my work said yes to my decision, and this Mary-Jane Gesing, Joe Sandberg accepted me as a postdoc. That's how I met the unfolded protein response. As Peter mentioned, it's an intracellular, this kind of insulin or insulin hormone receptor are folded in the ER. ER has many abundant molecular chaperones, but still, sometimes protein folding gets troubled. If in that case, this ER sends help signal to the nucleus. We are in danger, so we need help. Then nucleus makes a molecular chaperone mRNA and send molecular chaperone to the ER to help protein folding problem. So question is, if such signaling exists, there must be a sensor molecule. Also, some molecule induce transcription in the nucleus. And also, event in the ER must be connected, the event in the nucleus. At least three molecules is necessary for this signaling occurs. So we looked for the molecule and worked hard, and then identified first molecule, sensor molecule, and transcription factor, and how disconnected. Very surprised, to my very big surprise, almost at the same time, independently with Peter Walters. So question continues. If we understand each system, what happened, what's going on in the mammalian cells, then got a system in the mammalian cells. Then question continues. What's the role in our body is how important it is. To do that, we have to make a knockout mouse and the effect of deletion of gene to understand how important it is. So like my way in career is like take a risk and keep challenging, find the interesting question, and try to do my best to find the answer to find the answer to the question. It takes a long time sometimes. One answer for one mammalian transcription factor came 1 year later. The another, it took 5 years to get answer to second transcription factor. But finding answer to the important question is very, very interesting. So I hope you also can find important questions to which you want to have answers. And also probably it's very stimulating to find very good papers in literature. When I was a first year graduate student, Peter Walter published 3 papers back to back in one journal, one issue of Journal of Cell Biology, that he described how protein go into the ER. It was beautiful science. I was amazed by the result. So at that time, I want to do this kind of beautiful science in the near future. So I keep working hard, and probably awarding this Shaw Prize, I feel like I could do such a beautiful science, which I want to do at the beginning of my career. So I hope you can continue to look for good questions. Then do your best to find the answers. Thank you very much.
Thank you very much, Professor Mori. Please take a seat here on the stage. The discussion is about to begin. May I also invite Professor Walter, Professor Yang to take a seat on the stage?
All right, thank you both for very interesting, fascinating presentations. Again, we have another perhaps 15 minutes or so for questions, comments from the floor, especially young people. Question here.
As growth factors, it's kind of protein. Why are only protein but not glucose or other like fats that can attract the growth of cancer or other cells? I mean, they can act as a signal but not other molecules.
Could you repeat it, please?
Okay. In cancer, there are something called growth factor that can stimulate growth and angiogenesis. Yeah. But why are only protein can do this but not other molecules like glucose?
So in cancer, what happens is you have a lot of genomic instability. So basically, cancers have lost the ability to communicate. Cancer cells don't know when to die, right? So they divide in the wrong places. as a cause of the cancer. Because of that, because of their genomic instability and everything gets messed up, yet these cells grow faster and faster and faster. So they induce this response to help them grow, but they do not die as a consequence of it. So what we are trying to do right now is to go in and to try to develop molecules that hopefully can take this growth advantage away from them. And so that we want to reteach them how to die again. So the cancer is not caused by the unfolded proteins, but the unfolded proteins in this case give them this response that allows them to grow without the punishment.
While you are thinking up your questions, I have a few here. The questions I have here on pieces of paper seem very sophisticated. I don't know where they come from. So the first one, a misfolded protein called the prion causes mad cow disease. How is it linked to UPR, and what pathological changes are found in UPR?
You want to take that?
Prion proteins go through the ER. So it and then go through ER to the surface and then gets aggregated. Then cell broke the cell. That's called a sponge brain. And probably if we can manage the export of this prion proteins, we may be able to do something. We don't know for sure now. We need more research.
Thank you. Over here.
Hi. Hello, Professor Peter. I'm a final year student of chemistry student in Hong Kong. So I have a question. Before, like you, in my junior high school, I'm so interested in chemistry, about all the reactions, all the synthesis. But when I entered the college, I found, and do some junior research, I found, I lost in the technical problem. Like I'm doing some research on molecular dynamics or the modeling part. And I found many physicists just entered to this area. But I'm found myself getting lost in my chemistry. So what's the role of chemists in the biophysics or the biology research area? So yeah, I'm now applying for graduate school. I wait for your answer. Thank you.
I think there is a lot of roles for many different disciplines that come together now, and probably have historically come together in many different settings, right? But cells are basically carrying out the same chemical reactions, right? So if we understand what's going on in the chemistry of an enzyme, enzymology is a fantastic aspect. It's simpler chemistry because all happens in water, but it is very sophisticated. So your chemical thinking allows you to enter biology or to ask biological questions, address biological questions with a very unique basis. The same for physicists, right? You come into biologists with a physics understanding, you bring something very unique to the field. The same with math. We have vast amounts of data now, so we need to handle high throughput data sets and try to make sense out of them. A lot of that is done with mathematic modeling. So every subdiscipline can bring something incredibly valuable to the field. I think, as I said before, in graduate school, what you would like to find is a question that keeps you excited, as I think all the speakers here pointed out.
And chemical biology is now an important field, dealing with small molecules to find the answer to the biology question. So I think chemical biology is important. Also, one thing I jealous for chemistry is that it's more close to the application. once chemist has a nice compound or some material, it can be used more easily to the application system. In the case of our system, we want to find drugs to cure this UPL. But even though you have a nice compound, it works perfectly in the cell, but often the chemicals are inactive in our inside body. Or even it works in the animal model, it may not work in the human, or it may cause side effects. So it takes a long time to find nice drugs. It's one disadvantage of application biology, I think.
Perhaps we can try this one. You mentioned UPR as a potential mechanism of destruction of beta cells in type 2 diabetes. Are there any other diseases that can be explained by UPR, such as Parkinson, Huntington, and so on?
Yeah, maybe one of the most obvious ones is retinitis pigmentosa, where the patients have a mutation in the light receptors in our retina. This protein enters the endoplasmic reticulum, where it has to be folded, but because it has a mutation, the cell cannot fix it. So not only do you have now this receptor that doesn't function quite well, but the cell accumulates all this unfolded protein, gets frustrated, and goes down the cell death pathway that I showed you. So the whole retina degenerates as a consequence of that by cell death, leading to the inherited form of blindness in these patients.
Let's change tack a little bit and ask a slightly different type of question from these pieces of paper. Have you ever faced struggling in balancing various aspects of your life, career, family, health, and how do you eventually overcome it? Balancing different aspects of life, career, science, family.
As I already talked, my first thing was like I had a permanent position. I can work until retirement, but job is not interesting enough. Then I could not take a balance. A safe job, but this important. But many people can balance that things, but I want to do something more important. So just take a risk and went to the United States. And then next big thing is the competition with Peter. I was a postdoc, but suddenly I knew he is doing the same things, and he's already famous professor. He looks old, but he's only older by 4 years. But already he's a eminent professor. And even after I go back to Japan, I was still a researcher in an institute. But still keep working with Peter is quite a big deal. And it's very difficult to balance. After I went back, I had first child. And it's a lot of fun, but suddenly I realized the competition with Peter again. So I had to take this time to my kids. So it's quite difficult, but you have to manage to do both. Balancing is very important, I think.
Yeah, but Kazu is practicing martial arts, so we are scared of him too. This is actually a nice example that in science there's often different groups doing the same thing, but it's also diverse enough that this does not lead to any antagonism, any personal antagonism, right? We are still colleagues, we are still sending things, and we are still exchanging ideas with one another. And it's actually, it worked fantastically in our case, because whatever we did was confirmed in the other lab, and it moved the field forward a lot faster than if we had all been doing the same thing. Coming back to the idea of hard spots, well, a couple of years ago I came back from a meeting, and Patricia gave me a hug, and she found a little bump on my neck. So I was diagnosed with cancer a couple of days later. Everything's fine now, but it was an absolute terrible year. And I think the way you got through it is have many friends. We have a supportive environment at home, have in my lab, everybody helped each other. And I had wonderful colleagues that just kept everything going. So we got through it, and we move on, and I think we're perhaps even a bit stronger afterwards by having struggled that. Come on, there must be questions.
There are some questions here, but this one looks suspiciously well formulated, but it's nevertheless a good question. So let me simply read it. With self-retrospection now, what stages in your education shaped your scientific mind the most?
Education. I would say every stage. As was said before, right? We never stop learning, and it is one of the wonderful things of this career that you can constantly reinvent yourself. You constantly. I was a chemist, and I became a biochemist, working on the signal recognition particle. Then when we moved to UCSF, I became a geneticist and a structural biologist and a chemical biologist, and now we are working on all sorts of disease models. With the unfolded protein response, and each time you start fresh, right? You basically don't know what you're doing, and you start playing, and you make mistakes, and you learn from your mistakes. It's absolutely fascinating because it's never stagnant.
Yes, over here.
Professor Walkers, you have raised a very interesting question, interesting issue, but very realistic is the language barrier. And I think it's especially true for us whose mother tongue is not English. So compared to the time that when you are rejected from some of the state's university due to your poor English, have you a very dramatic improvement in your proficiency in using English compared to now?
I think the best thing is you go somewhere in an English-speaking country and find a girlfriend.
Wow, thank you. That's a good joke.
Yeah, in Japan, usually if you go abroad to be a postdoc, it takes 6 months to understand English. But in my case, it took 8 months. When I got into the UT Southwestern April, radio was always going on, but it's a noise, only noise to me. But 8 months later, in December, suddenly radio is a promoting commercial for the hospital. Suddenly I can, because we watch television every day. The caption is there. If we buy some equipment, that helps to understand what's going on. And also I play kendo, and there was a kendo player there, and then I joined that team, and then master of the dojo practice team asked me to instruct American people. So I always think of how this Japanese style training to explain to American in English, that helped me. Just use English. That helps you. So now I'm in Japan, and I don't use English, so my ability in English is going down.
But about a year, I would say, then you're fine.
Any other questions? That allow me to ask perhaps the fight. Oh, okay, then, yeah, good.
Good afternoon, professors. Thank you for your interesting and informative presentations. I'm a student representative from the Hong Kong University of Science and Technology, and I'm wondering if, when you do scientific research on biology, it is inevitable to manipulate some kind of organism. And for example, when we are inventing some kind of medicine, we need to carry out clinical trials on human. So will it affect your conscience, or will it disobey your moral values when something goes wrong in an organism, which makes them suffer or something like that? Can you tell us more about them? Thank you.
You mean So we started, both of us started the unfolded protein response in yeast cells. And when yeast cells, I don't know how we would tell whether they suffer or not. So no, there's no moral issues whatsoever. As you work with mammalian systems, you tend to start with cell lines, so cell culture. Again, there are no ethical issues involved there. And then when you try to really address disease models, you have to go into animal models. And you try to think very hard of the experiments so you don't overdo and do stupid things with mice, for example. So I think it becomes progressively more important to be sure that you do experiments with the intent of getting clean answers and thinking about it a lot more ahead of time. Otherwise, it's just unavoidable, right? We have to go into animals in order to make any difference with clinical applicability.
Right. Let me ask one final question then. Your work has led to very important applications and even more important potential applications in the cure of diseases. Did you start out with this sort of motivation in mind, or were you just driven by curiosity, just to understand some mechanisms?
So I started out completely curiosity-driven science. We started to ask a very simple question: how does one part of the cell knows what's going on in another part of the cell? How is that information transferred? And all the surprise, so all that, again, we heard that before, right? Focus on understanding, not on the discovery. Discovery comes by serendipity. She helps you along. You're observing things that suddenly don't make sense, and as things don't make sense, then you learn how to resolve these paradoxes. And once you have a resolved paradox, the answer cannot be boring. So that's being noticed, that's being published in very prominent places. And then whether it's applicable, it's an enormous amount of work to find that out, right? And to see, we are talking about a very basic pathway here that is present in every cell. Now, for different diseases, the outcome could be very different. We need to go into these models to now figure out where there is a therapeutic window where we can actually do more good than harm to the organism. And that is not predictable, even at this stage. We have not cured any disease. We have advanced knowledge, and we have the hope that this will help us to cure some diseases. I mean, viruses use this pathway. So with some of the molecules that we've been developing here, maybe we have something in hand already that could be developed into something to help with the Ebola threat or with other diseases that come along. So we'll just have to try. We keep on trying. We explorers.
After I met UPR, I always have an interest question in front of me. I want to get answer to the question. What's the mechanism in each cell? Understand the mechanism in each, then want to know mechanism in the mammalian cell. Then understand the mechanism, then want to know the importance in the entire body. Then, but still, we find answer only for one or two molecules. But each has only one sensor molecule. But we have 10 sensor molecules. So during evolution, the number of sensor molecules keep increasing. So why we need so many sensors? There's a curiosity-based question there. But after finding this kind of question, we may be able to answer cure diseases. So then also one dear thing in the United States, the USA has Howard Hughes Research Institute. Then President Howard Hughes are basic researchers, and still claims importance of basic research, but now Japan Prime Minister Abe is focused on only economical growth, and, much more money on application, and so we have to balance basis and application to get some money. So I cannot say Peter can do only curiosity-based work, but we have to do both to survive. It's quite difficult days for basic research in Japan.
Well, I think we have really overrun quite a bit, but it's been a most fascinating discussion. So thank you again, Professor Walter, Professor Mori.
Thank you, professors, for sharing with your experience in doing research. Please take a seat on the floor.
And thank you all for coming.
Meet the Shaw Laureates 2014 Popular Science Forum is now concluded. Once again, we would like to thank the Shaw Laureates for sharing their challenges and joy of doing science with us, and Professor Yang for moderating the forum. Thank you, audience, for joining the forum in this afternoon. Thank you very much.